So I don't really know why they cared if it was women on a high school tennis team, but hair color, what scale would we be talking about? What level of measurement? This is going to be nominal. So if I'm saying hair colors, we're just naming things. Okay. Now, B is tricky because it is a number. Numbers on the shirts on, again, I don't care if it's a girls' soccer team. That doesn't matter. Soccer team. Numbers on the shirts. It's a number, but here's the question. If you are number 1 on your shirt, does that mean you're a better player than if you're number 2 on your shirt or number 13 on your shirt or number 69 on your shirt or number 72 on your shirt? It has nothing to do with anything. The numbers on the shirts are being used like names. And so even though this is numbers, these are still nominal. And that's a part that can be a little bit tricky for people. Ages of students in a statistics class. Ages. Now, here's what matters. Ordinal tells you things can be in order, but zero doesn't, that's not really a thing. Interval means that you can have a zero, but the zero is not the lowest you can go. Ratio means you have a zero and it's the lowest you can go. Can people be negative 2 years old? So in this case, you're going to have ratio on here because ages are a thing where zero actually means it's the starting point. So if zero is the starting point, then we're on the ratio scale. Okay. Temperatures on 22 selected refrigerators. I've used temperature a bunch. Temperature is the one that's interval scale. It has a zero, but we can go below that zero. Number of milligrams of tar in 28 cigarettes. Yeah, that's ratio because zero actually, if you have no tar in them, that's the starting point on counting for tar. So this is ratio. Good. Number of pages in your statistics book. Can you have 0 pages? And that kind of sounds like a trick question, huh? That one's going to be ratio. Theoretically, there's technically a possibility you could have no pages in a book. It would just be a real dumb book, wouldn't it? Marriage status of faculty at a community college. Nominal. So that'd be like single, married, divorced. Those are things we're naming. Okay. List of 1,247 social security numbers. If your social security number comes before somebody else's social security number numerically, does that change anything about who you are? So ordinal doesn't make sense for this. Can you have a 0 in your social, like the actual social security number can't be 0 and you can't have a negative social security number? None of that makes any sense. So social security numbers are actually working like a name. If I say your social security number, like that's you. It's like your identity. We've named you with that thing. So this one would actually be nominal, which is super weird. Ratings of a movie from poor, good to excellent. That one's also nominal. Nope, it's not nominal. Ordinal. Sorry. My brain is like not working at the same speed as my mouth this morning. Do you ever have that happen where you're like, I did not mean to say that and it still came out anyway? What the heck? Final grades, A, B, C, D, F for students in a chemistry class. So if an A student ranked different than an F student? So that's ordinal because there is some sort of ranking happening there. Good. Salaries. Can you get a negative salary? But could you make $0? Yeah, so this one's going to be ratio. Zip codes. Yeah, this one's going to be nominal again. It's numbers, but the numbers are naming where you are. The nationalities listed in a recent survey. That one's definitely nominal as well. It's easier when it's actually like a category, but when there's numbers, things can still be nominal. And the amount of fat in grams in 44 cookies. Yeah, ratio. Good.
Could you explain ordinal like more thoroughly?
Yeah, so ordinal means there's a ranking happening. So ordinal can still be just words instead of numbers. So it could be that it was poor, good, excellent, but those words I'm using still have some kind of like natural order to them. Usually with ordinal, it'll be like first, second, third. We know for certain that there's an order there, but you can still have things like best and worst kind of thing. But if it's just a word, it's definitely nominal. But numbers can still be nominal if the numbers are being used as a way of just naming a thing. It's not really giving you an order. So with the like zip codes in there, it's numbers, but like the zip code isn't naming like, oh, well, you live to the right of this person. It's not giving an order to it. It's just giving a location. They're kind of tricky. So those were some good examples to kind of go through. The sampling stuff also gets to be a little bit tricky. So I wanted to make sure we had some examples of that in case you have to like try and name what kind of sampling happened. Random sampling is what it sounds like. It's completely random. But in terms of the other types, stratified sampling versus cluster sampling. When it's a cluster, you've divided the population into different groups and you're randomly selecting those groups. Everybody in that group is part of the cluster. Versus stratified sampling, there's some sort of proportion happening. So like you're trying to have 2 times as many women in the group as there are men, or you're trying to have exactly the same number of Democrats as Republicans to keep a sort of ratio happening. That's stratified sampling. So cluster sampling doesn't have anything to do with you preserving a ratio. It's you actually having groups and then surveying everyone in the particular group. Systematic sampling is when like you're taking every 100th person or something from a group. So you're being very systematic about who you're picking. Or like if we were talking about like the gym membership thing, and it would be like maybe you stop every 3rd person and ask them a question. You're being systematic about it. Convenience sampling is like, it might not be the best place for you to get the stuff, but it was convenient in the moment for you to use that grouping. So let's look at some examples. This might make a little bit more sense. So we're just going to identify things as random, cluster, stratified, convenience, or systematic sampling. Every 5th person boarding a plane is searched thoroughly. Systematic. So because I'm doing every 5th person, I have a system going. This one is systematic. Good. At a local community college, 5 math classes are randomly selected out of 20 of them, and all of the students in each of those classes are interviewed. That's the example of a cluster because I took groups and everyone in that group got questioned. That's cluster sampling. A researcher randomly selects and interviews 50 male and 50 female teachers. Yeah, so this one I'm trying to keep a proportion that's even. And so by going 50-50 on this one is going to be stratified. A researcher for an airline interviews all of the passengers on 5 randomly selected flights. So each flight would be a group, and I did everybody in the group. That makes it a cluster. Based on 12,500 responses from 42,000 surveys sent to its alumni, a major university estimated that the annual salary of its alumni was $92,500. This one's random because there were 42,000 surveys that were sent out, and we were equally likely to select any of the people to consider what their response was. They just selected 12,500 out of that. That was completely random. So this is random sampling. community college student interviews everyone in a biology class to determine the percentage of students that own a car. That's convenience, because students who own a car, like your biology class, is probably not like going to be exactly the perfect way of finding that number for students in general, but it's a group of students that you might have had available to ask. So this would be called convenience sampling. All right. A market researcher randomly selects 200 drivers that are under 35 years of age and 100 drivers that are over 35 years of age. That's stratified because I'm trying to preserve some ratio. So because they were being so specific about how many they had, this one's stratified. Good. Of all of the teachers from 85 randomly selected nation's middle schools, oh, sorry, I said this backwards. All of the teachers from 85 selected schools were interviewed. Yeah, this one's a cluster because the groups are the schools and we did everybody in the school. So that still makes it a cluster. Sorry, I read that wrong the first time. To avoid working late, the quality control manager inspects the last 10 items produced that day. So is this the best way for him to check how things are? Nah, but it was convenient for him. So this is a convenience sampling. The names of 70 contestants are written on 70 cards. The cards are placed in a bag and 3 names are picked from the bag. Yep, that one is random sampling. Good job. Good, good. So I hope that helps a little bit because there's so many different definitions on here. So it's good to just sort of practice what types of things they might ask you. Do you have a question?
Would this be simple random or just random?
In terms of what I asked in terms of categories, I just put random, but simple random. Yeah, that would be a simple random sampling. Good job. All right. These next ones, I'm not asking you like a question really, but I wanted to review skewness. So this is not skewed. This is beautiful. This is what we call symmetric. It's also unimodal, means it has one mode. You can have 2 modes on a symmetric one. What would happen would be these 2 bars would have to be higher than the middle bar, and then it could be bimodal, and it would still be symmetric as long as these 2 bars were still the same height on either side of it. Symmetric just means it's basically even on both sides. Like if you were to cut it right down the middle, this side looks the same as this side. So this is a symmetric sample. In a symmetric sample, your mean should equal your median. Okay, so in a symmetric sample, your mean is equal to your median. So in this particular case, because it's unimodal, the mode is actually the same as well, but this is going to be mostly important that the mean and the median are the same when it's symmetric. That's important. Okay, but then this was the question people were asking me in office hours. Looking at this picture versus this picture, this one is called left skewed or skewed to the left because the tail, the lower tail is coming out to the left side. So this one is skewed to the left. And the question that they were asking was, it was asking just sort of randomly, if it's left skewed, is the mean or the median higher? And they were like, ugh. So left skewed, the mean is less than the median. In a left skewed distribution, the mean is less than the median. This is an example of a right skewed distribution because the tail is off to the right now. And the mean is the largest, or the mean is bigger than the median. So the mean is the largest. The mode is the smallest on this one, but the mean is larger, or mean is larger than the median. is kind of the most important part there. How are you going to remember that? You could like totally give yourself numbers and do calculations, but on a test, that's probably going to be hard. So here's what I came up with. It's not great because this is just Jen trying to come up with something for you to help you remember. So skewed to the left means less. Left means that the mean is less. So I'm talking about the mean because the mean is kind of the big important money. Mean is the big important word. Is that what I wanted? Skewed to the left. Left means the mean is less. Skewed to the right, I decided the mean's got height. The mean is bigger. Does that make, I don't know. It needed to rhyme in order for it to be maybe something you remember. So left, mean is less. Right, mean's got height. Mean is bigger for this one. If that helps, cool. If not, you got to come up with something because I seriously tried and I asked people in the office and they laughed and they're like, I got nothing, Jen. And I was like, no. So some way of helping you remember it. I like that left, the mean is less, started with the same letter. That made me happy, but I was wishing the other direction helped. So aside from that, I had a bunch of people come see me about some problems that were probability problems that it looked like Whitener gave. And I imagine they'll be good for Lang as well because probability problems are ones that usually people are like, "Blah." So I changed up the words a little bit because there's just so many dang words in these problems, but it's the same problem, I promise. The likelihood of a particular crime being committed is 2%. If a person really did commit the crime, we're going to call that C. The probability they're found guilty, we're going to call that G, is 99%. If they did not commit the crime, they're 98% likely to be found innocent. So I feel very bad for the 2% that are found guilty. So we want to find the probability if a randomly selected adult is found guilty, then they actually committed the crime. We want to find the probability that a randomly selected adult is found guilty and did not commit the crime. And we want to say, are the events guilty and committing the crime independent or dependent? And we're not just going to do it based on our intuition. We're going to do it mathematically. My hint to you when you're doing either mutually exclusive or independent on these exams is don't try and reason through them using your logic. Use the math formulas for it because sometimes the logic, in particular on the one that had to do with the engineering students, if you tried to logic through it, you got the answer wrong, I promise, because my logic got me the answer wrong. You can't do it with logic. You must do it with the math. So probability of a randomly selected adult, if a randomly selected adult is found guilty, then they committed the crime. So this is a conditional probability problem, right? So if we want the probability that given they are found guilty, that they actually committed the crime, that's probability of C given G. So given that they're found guilty, what's the probability they actually committed the crime? Okay, I'm going to go ahead and just write the thing we're finding for number 2 as well, so that then we can kind of feel out like what sort of formulas are we going to need here. Find the probability that a randomly selected adult is found guilty and did not commit the crime. So we've got an and in there. So probability that they're found guilty and, so that's our upside down U, they did not commit the crime. Are you cool with me writing C with a complement after it? Or you can do the little dash mark if you prefer the dash mark. You could also put I for innocent. That's also cool. Actually, you probably shouldn't because then guilty gets to be confusing. Committed the crime versus guilty and innocent. That's why I'm writing it this way. It gets confusing. All right. what did they actually give us in this question is important. So we should figure out what they gave us. They gave us the probability of a particular crime being committed is 2%. So probability of C is 0.02. So that means that the probability that the crime is not actually committed, so the complement of that would be what? Yeah, that's going to be 0.98, because we'll do 1 minus this one. We'll give you that one. All right, so we got that. Then they said that if the person really did commit the crime, so this is given that they did commit the crime, so probability that given that they did commit the crime, so given C, that they are found guilty, that's G given C, they're telling us that that is 99%, so 0.99. So at this point, sometimes people like to make kind of like a little tree of things. Have you seen any of the trees for the probability yet? Some people are nodding, some people are not. So 2 things could have happened. Someone committed the crime or someone did not commit the crime. So that would be the C complement. If they committed the crime, we have 2 different things from here. The probability that given that they committed the crime, that they're actually guilty, we just said that that one is 99%. So there's this other probability, given that they committed the crime, that they're not actually guilty. That would be guilty complement. So given that they committed the crime, but that they're found innocent is basically what that would mean. What's that probability then? Yeah, that's a 0.01. And so sometimes doing this with a tree makes this a little more obvious because you're like, oh, well, yeah, that has to be the case. Now, let's say, given we're starting with this idea that someone did not actually commit the crime. So given that we know that the person did not commit the crime, 2 things could happen. They could be found guilty. Guilty given that they did not commit the crime. We weren't like specifically given that number. But we were given this other number. So given that they did not commit the crime, that they would be found innocent, that would be guilty complement. They told us in the problem, if they did not commit the crime, they're 98% likely to be found innocent. So this one, we actually got. So given that they didn't commit the crime, what's the probability they're found guilty? 0.02. Okay, so we're going to need some of those things to help us answer this question, because this one ends up being one of those Bayes theorem problems. C given G, we've got G given C. We've got the backwards one. And so when we have the opposite of the thing we want, this is usually going to be a Bayes theorem question. So here's how I'm looking at this. If I want the probability of C given G, but I've got the probability of G given C, then Bayes' theorem says that I want to then multiply this by the probability of this denominator piece here over the probability of G. And so this is your theorem that we have. And some of those numbers we've got already, and some of those numbers we don't quite have yet. So we have to actually look at what we've got. So G given C, I have that one, that's 0.99. Probability of C, I have that one, that's 0.02. But probability of G, I don't have up here. So we would have to find the probability of G using that weird rule where I use the probability of C and G plus the probability of C complement and G. And so then the C and the C complement parts will cancel when we do this. So this is what we were doing last week where I was like, these ones are kind of weird. And it would just leave us with the probability of G. So we have a formula that helps us write this thing out. So this is the same thing as the probability of G given C times the probability of C. We have the probability of G given C and we have the probability of C. So that's good. And then this one would be the probability of G given C complement times the probability of C complement. And probability of G given C complement, we have that number and we have the probability of C complement. So we have everything we need in order to find just the probability of G. So mathematically, we're just plugging our numbers in. G given C, we said is 0.99. P of C is 0.02. We're going to add that to G given C complement. G given C complement is 0.02 times the probability of C complement. That's 0.98. And so now that's just a calculator question. So I got 0.0394. Okay. So then you're like, cool, Jen, are we done? No. So what we just found was the probability of G, which is the denominator on the thing that I need. So this is going to be the denominator here. So we need to plug in to the formula up here. The probability of G given C is 0.99. The probability of C is 0.02. And now we're plugging in our 0.0394. So I got 0.503. I'll just leave that as 2 decimal places because they were giving us 2 decimal places for this. So 0.50 is going to be our answer to the question that they actually asked, the probability of C given G. So you can see how on a test, this could really, really mess with your head if you're kind of a little bit nervous about what it is that you're finding. So my recommendation for you on these types of problems would be read through it and write out what you have from the get-go. Maybe make yourself a tree to figure out all the different things you can get without having to really think all that hard, because making the tree didn't really take that much time and it gave us 4 things right there that were really useful to us in the formulas. And then I would dive into what the question's asking to see what you can get, because if you have at least that much stuff on there anyway, lots of partial credit can come your way because you're showing that you understand the process, even if you didn't completely get there. If nothing else, get the formula on the sheet. the correct formula for the thing that you're looking for, because that lets them give you at least some partial credit. The next one isn't quite as bad. So we want the probability of G and C complement. So this one, your formula on this, when you want an and, that's going to be your probability of the first thing times the probability of the C complement given the first thing. So that's straight off of just our formula sheet. So do we have those two things? The probability of G we had to get when we were trying to solve for the first thing. So we have the 0.0394. That's our probability of G. And then the C complement given G, let's see, C complement given G, is that a part that we have yet? We don't have. That one, can I turn it around? Do we have it if I turn it around then? Probability of C complement, we do, and G given C complement. So we do have it if I turn it around. So you see how I got stuck because I didn't actually have this one when I looked through my list? Or you're like, Jen, what are you doing? I have no idea. So here's why I got stuck. The way I originally wrote this, when I looked at our formula, the formula sheet said, put the probability of the first thing and then take the second thing and put it first, then given the first thing here. When I did that though, and that this is what I ended up with, the probability of G we got in the last part of the problem. So I had that, but then probability of C complement given G, I have exactly the opposite of what I need. I have the G given C complement. I don't have it in that direction. But when this is an and sign, do you agree that that's the same thing as the probability of C complement and G? If it's an and, can't I just turn those around? So with an and, this I could rewrite it with the C complement first and then the G. So that means that I'm allowed to do this in the other order, which means this would be probability of that thing first times the probability of G given C complement. And then that actually helps me. So this one, I didn't have the whole thing that I needed. I only had the first piece, but now I actually have both pieces. The probability of C complement we said is 0.98. And then G given C complement we have is 0.02. So sometimes you're going to have to do that in the middle of a problem. You'll look and you'll go, I don't have the one that I wanted. But now 0.98 times 0.02, that's going to be 0.0196. So if we were rounding that to 2 decimal places, we'd say that was 0.02. We got that one. Okay. And then the last question says, are the events guilty and committing the crime independent or dependent? And we have to justify our answer. So looking at what we have for our rules for independent events would mean that the probability that we're guilty times the probability that we committed the crime is supposed to equal the probability of guilty and committing the crime. That should be true if they're independent. So probability of G we got was our 0.0394. Our probability of C we have is 0.02. And so my question is, I'm going to put a question mark above that equal sign. If that's equal to the probability of G and C, then we're good. So G and C, if we need to do that calculation, that's going to be the probability of the G times the probability of C given G. So probability of G 0.0394. So that's the same as the other side. And then C given G, C given G, is that one that we have? Nope, we have G given C, so we gotta do it backwards again. Man, we have lots of practice with the backwards. Probability of C times the probability of G given C, we do have that one. Probability of C is 0.02. And probability of G given C is 0.99. Okay. Now, without me even putting this into the calculator, we have 0.02 on both sides here, and then I'm multiplying by a different number here, so they're definitely not going to be equal to each other. You can put it in the calculator, but they're not going to be the same. Question?
Isn't there like a test where you set it to 0 or something?
That is if it's mutually exclusive. So I'm glad you said that. That's the wrong test for independence. But you're absolutely right. If it had said, are these things mutually exclusive? Then you would see if the and was equal to 0. So you've got the correct thing for the other thing for mutually exclusive.
But isn't there one that is like, if like P of G is not equal to P of C, then it's not like independent?
It's related to this formula here. You can take each of these parts and break it into 2 separate pieces, but ultimately this is the test you're doing. So you're right. There's a different way that it could look. In this particular case, you're going to end up needing the full formula. But you're right. There is some other ways that it can look. So the way the rule is written for independence, this is the rule that I'm using, but it breaks down into these 2 separate rules. So that's, you're probably thinking, can't I just do this or can't I just do that? And it's the same as this rule right here. It's just broken into 2 parts.
Okay.
But you're right. Yes. And then the one you were thinking of is the mutually exclusive. Yeah. So in the end, these do not end up being the same. So I put the question mark above it. They're not the same. So this is not independent, or you can say dependent. That means the same thing. Not independent. Okay, we'll see how quickly I can get through the other one. An engineering school reports that 55% of its students identify as male. So that means 45% of them identify as being something else. To make this problem easier, I'm going to say just female. But like in the real world, you can identify as more things than just male and female. When we're doing statistics problems, they often like to do male and female, like those are your only choices. That's wrong and totally backwards. But I also understand that they're trying to make the problems not insane. So I guess in some ways we appreciate that, but it's still, they could identify as other things. So to be specific, I'm going to say 45% of them identify as being female. 40% of its students were between the ages of 18 and 20. We're going to go ahead and call that event A, even though that'll be age. We'll use that as the age event. And that 25% were both male and between the ages of 18 and 20. So let's write down what we've got. Probability that they've identified as male is 55%. So for female, I'm going to put probability of male complement. And the reason I'm going to do that will make sense when I go to answer part C. That's 45%. The other thing that we've got is the age probability. So the probability that they're between 18 and 20, we're saying is the probability of A. They told us that that's 40%. And then they gave us that the probability that they're both male and between these ages. So probability male and between 18 and 20 is 25%. So these were the things that we were given for free in the problem. And the first question says, what is the probability that a randomly selected student is male or between these ages? So male or has the U in between. Okay. Our formula for that one is the probability that they're male plus the probability that they're in that age group minus the probability that they're both male and in that age group. And they gave us all three of those numbers, so this one shouldn't be too bad. So probability that they're male was 0.55. Probability they're in that age group was 0.40. And they told us the probability that they're both of those things is 0.25. Yeah.
So I was done the chapter, I think it's either 3 or 4 homework yesterday. And like I was trying, because one of the questions was like asking for the or of like 2 things. And I tried using the formula, but then it told me I got it wrong, and it was saying like, oh, it's independent. So
If they're independent, the rule is different. And the reason that I'm going to ask you, are these things independent in the very next step, is to prove to you that we use the correct formula. So exactly what you're asking. If they were independent, I would have to use a different rule, but they're not. And we're going to find that out in part B. They're not independent, so that's why it's this rule. So this one, when we add those up, we're going to get 0.7. If they were independent, we would just be adding those 2 things together and not subtracting off where they're intersecting. But in this particular case, I'm going to tell you for certain that we use the right formula by calculating if these things are independent. So in order for them to be independent, then we would be using our independent calculation again, which would be the probability of M times the probability of A, and we're checking, is this the probability of M and A? They would have to be equal if they're actually independent. Probability of M, they told us, is 0.55. Probability of A is 0.40. And I'm going to put an equal sign with a question mark. Is that the probability of M and A, which they told us is 0.25? So 0.55 times 0.40 is 0.22. So that's not equal to the 0.25. And so because of that, I know these are not independent. So that's why I'm positive we use the right formula. Okay. It is exactly 10:50. So if you have to go, it does not hurt my feelings at all. I'll try and finish the last 2 parts before I actually take off. But if you have to go, I'll post the video. So it's okay. What is the probability of a random student being female who is not between the ages of 18 and 20? And so here I'm going to use something that you might be like, why are you not using probability of F for female? Well, if I want the probability that the random student is not a male, so that would be male complement, so there's our female, who is not between the ages of 18 and 20, so this is an and then it's not in that age group. What I have right here is one of De Morgan's laws, and that was on the formula sheet for folks. One of De Morgan's laws said that if I had the intersection of two complements of something, that's the same thing as the complement of the or statement of those two things together. So this should be the probability of this complement. So if I want the complement of both of those things, that's the take the M and take the A with the or in between and take the complement of that thing. The complement of that thing is, we calculated that thing in part A. So I'm going to do 1 minus this thing. So it's 1 minus what you found in part A, 1 minus 0.7, which comes out to be 0.3. So this right here is De Morgan's law or De Morgan's rule. So if you want the complement of both of those things, you take the or statement for those things and take the complement of that. That's De Morgan's law. Are these things mutually exclusive? This is the other rule. This is the one with the 0. So if they're mutually exclusive, what I am calculating is that I want the probability of M and A to equal 0. That's the rule if they're mutually exclusive. The probability of M and A is going to be us using our probability of M times the probability of A given M. A given M is not on our sheet, so let me do that one backwards. Let's see, do we have the other piece? M given A. Given that there, I don't think I've done any of those calculations yet, have I? Oh, sorry. I did the calculation of M and A earlier. We don't need that part. Sorry. That was part up here, 0.25 was given to us. Sorry. Way easier. Just 0.25 was given to us for the M and the A. So 0.025 is not equal to 0. And because of that, these are not mutually exclusive. All right, I promise I'll do some binomial theorem stuff on Friday. My Friday testers, good luck. And if anyone wants to come see me in office hours today, I am over in the EOP cottage from 2:30 to 3:30. So I could also help with binomial theorem stuff then if that's a time that works.